Good morning and happy test day. It is test day, all right. And so what we're going to do is we're going to take a look at this study guide of sorts. You know, all the review problems in chapter 1 and the chapter 1 test at the end of the chapter. Make sure you feel confident about them. I think that all these problems are straightforward and simple. We talked about some of them, but just in case anybody missed any of them, I want us to be clear about exactly what's going on here. So let's start. We've got this first one. It says you've got to come up with, if you're given the angle 70 degrees, they're just asking, making sure we understand some real basics, like what's the complement of 70 degrees and what's the supplement? Well, the word complement comes from the idea of complementary, which means two angles add up to be 90. So what's the complement of 70? Well, that would be 20 degrees, because 20 degrees and 70 degrees add up to 90. Supplement, same way, is of supplementary angles, which are two angles that add up to be 180. So if one of them 70, well, then the other angle would have to be 110. A little point of fact worth noting is that complementary and supplementary angles are always 90 degrees apart from each other. Because for complementary angles, you're looking for 2 to total 90. For supplementary angles, you're looking for the 2 to total 180. So because these two numbers are 90 apart, these two numbers will always be 90 apart. Just worth mentioning. But so this was just really review to make sure you understand these ideas and concepts of complement and supplement. Okay, moving on. This was a right triangle, not identified as a special right triangle, but anybody who was kind of looking at it would notice what Zach mentioned the other day, and that is the fact that a short side is exactly half of the hypotenuse means that this has got to be a 30, 60, 90. It's the only kind of right triangle where you could have one of the short sides be exactly half of the hypotenuse. And so if that's the case, then if I know my 30, 60, 90s, then I know I always take the short side and multiply by the square root of 3 to get the longer leg. So therefore, this would be 3 times the square root of 3. Now, let's say you didn't notice that. That's no problem. It's still a right triangle, and you've been given two sides. And so you could use the Pythagorean theorem and say, well, I know that 3 squared plus x squared is equal to 6 squared. And that would mean that 9 plus x squared is equal to 36. And then you subtract, and you get x squared is 27. And at this point, you guys all might think I'm a big fat liar, because all of a sudden it says x equals the square root of 27. You said, well, it was supposed to be this. Well, those are the same number, because realize that 27 is 9 times 3, and I know that the square root of 9 is 3. So that means the square root of 27 is the same thing as 3. I'm getting a little sloppy here. We know that the square root of 27 is the same thing as 3 times the square root of 3. Okay? And so we can see it either way. You can use special right triangles and come up with its answer. You can use Pythagorean theorem and come up with this answer. Either way, you're going to get the same answer. Okay? All right, this next one, there's definitely a problem very similar to this on the test, and so you should understand and know how to do this. This problem starts off with the idea is, I just realized I didn't write down right here what number it actually gives us. But what it does is it shows us how you could bump two special right triangles up against each other, and from that information, you should be able to figure out all the sides. The challenge with this one is, of course, knowing what to do when you're given something, like in this case, we're told that s is 5 times the square root of 3. So that's this side right here. Well, these are the two sides of the 45, 45, 90 that are the same length. So therefore, h, of course, then has to be 5 times the square root of 3. R has to be 5 times the square root of 3 times the square root of 2, which you multiply those two things, and you get 5 times the square root of 6. Pretty simple. Then we moved over, okay, if I know what h is, and I know that h, and this, they're making it so simple, that h is 5 times the square root of 3, this is the longer leg of a 30, 60, 90. So to go from the longer leg of a 30, 60, 90 to a shorter leg of a 30, 60, 90, then you get to divide by the square root of 3. Well, that makes y very simple, because that means that y is going to be 5 times the square root of 3 divided by the square root of 3. These two cancel out, and we just get 5. And now I know the short side of a 30, 60, 90, and I just have to double that to get to the hypotenuse. So therefore, x has to be 10. Super duper easy problem. I'll be honest with you, the one on the test is not as easy. I chose to make things not come out quite that clean because I wanted to make sure you knew how to deal with radicals. Okay, that's something we got to always make sure we know. All right, let's see. This next one, and I'm sorry for this next one, if you are having a hard time seeing this image and kind of understanding it, please understand we've got two right triangles. There's one right here, and this right triangle is really kind of like, I want you to picture it's laying down on a table, okay? And the table looks like this. And so that one is laying down on that table, okay? I'm going to try to draw a little bit of the table here so we can kind of understand. And the other one is standing up on the table, on edge. And so one is laying down on this table, and the other one is standing up on edge. And so with that, neither right angle really appears to be a right angle in this picture. And so it can be a little challenging to kind of understand what they're asking. But for this one, it says, okay, we got these two right triangles. The length of DB is what we're looking for. Okay, find the length of DB. What we're told is we know that DA is 6. So that's this side back here. They're told that that's 6. We know the length of AC, which is that hypotenuse on the one laying down, is 5. And we know that BC, which is this little short side on the one laying down, is 3. Now, realize this whole thing's not drawn to scale because there's no way at all that this big long side right here would be 5 and what appears to be a relatively short side would be 6. So clearly this is not drawn to scale. I can't get too overwhelmed by stuff like that. All I got to do is follow basic Pythagorean theorem and go, here I've got, on this one laying down, I've got two sides given me. One side is 3, one side's 5, so I can figure out this other side. Once I do that, I've got two sides of the triangle that's standing up, and I can figure out the third side. Because the goal is I'm trying to figure out that hypotenuse, that DB. So I know that x squared plus 3 squared is equal to 5 squared. X squared, 3 squared, can you give me 5 squared? So that is x squared plus 9 is equal to 25. Subtract the 9. X squared is 16. Take the square root, and x is equal to plus or minus 4. But it's got to be positive 4 because it's the length of a side. Then the next one, you go, okay, so 6 squared plus 4 squared is equal to, we'll just call it h for hypotenuse, squared. And that means that 36 plus 16 is equal to h squared. That would be 52 is h squared, which would mean that that hypotenuse, or that length, I think it's dB, isn't that what it is? dB, is equal to the square root of 52, okay? Easy. All right, number 6, super easy problem. Hopefully you know your special right triangles. Hopefully you've kind of looked over those. It says that the longest side on a 30, 60, 90. Well, the longest side is the hypotenuse. And the longest side of a 30, 60, 90 is 5. So therefore, that short side is always half of that. So that's going to be 2.5. The longer leg is always the short side times the square root of 3. So this would be 2.5 times the square root of 3. You could also have 5 halves times the square root of 3. You could have 2.5 times the square root of 3. I mean, you can have all different ways of writing the exact same number. I think that maybe this one makes the most sense, but whatever. All right, now we get into something a little bit more interesting. All that stuff was really basic, Pythagorean theorem, special right triangles, angles within a triangle. That's really basic. So now this is the first time we actually saw problems exactly like this in advanced algebra. I don't know if anybody remembers, but we did these problems. And so this was just a good throwback to that. And it says, okay, so if you got this one point at negative 2, 3, so let's think about where negative 2, 3 would be. 1, 2, and then 1, 2, 3, somewhere around here. And then there's this other point that's at some x value and then 1. So we don't know where it's at, but we know it's the y value of it is 1. And it says, okay, we want to find out what x value would this have to be so that the distance is square root of 13. Well, if you take a second to think about this, you're going to realize you're going to get two answers. Because you could be somewhere right here, and this could be the distance, square root of 13. Or you could be this somewhere over here, and that could be the distance, square root of 13. And so there's going to be two answers. So in theory, there's this one point over, there's one point over here that it could be, and there's one point somewhere over here that it could be. Now, that picture's not drawn to scale. Those are just kind of guesstimates. But either way, what we need is we need the distance formula. And the distance formula is that distance is always equal to the square root of the difference of the x's plus the difference of the y's. Each of those have got to be squared, and then we take square root of the whole thing. All right? So what I'm going to do is I'm going to write that formula. And then I'm going to plug everything in. We're told the distance is the square root of 13 is equal to the square root of, let's do the difference of the x's. X minus a negative 2 would be x plus 2 squared plus 3 minus 1 squared. Now, some people are going to freak out the fact that I did x minus a negative 2, but then on this one I did 3 minus 1. The order doesn't matter because we're going to square things in the end, okay? Order matters in subtraction because if you change the order, it changes the sign. But if we're going to square it, negative 4 times negative 4 is the same as 4 times 4, so it doesn't matter. All right. Now, I've got a radical on each side, and so at this point, what I would do is I would say, well, let's square both sides. And that's going to give me 13 is equal to x plus 2 squared plus 2 squared. All right. At this point, you can say, well, 13 squared is equal to x plus 2 squared plus 4. You could subtract 4 from both sides, and that would give you that 9 is equal to x plus 2 squared. All right. Hopefully everybody sees that, and hopefully nobody says, well, x plus 2 quantity squared is x squared plus 4. That's wrong. And that's a conversation I've been having with some of you daily. But let's make sure we understand that that is wrong. What I see at this point, my way to do this is to typically FOIL this part right here, which honestly takes way more work than what we need it to take. We just don't need to do all that work. The easier way to do it, and we'll call this the Parker-Jordan method, because it's what he suggested to do, and that is you go, well, I've got x plus 2 squared equals 9. Let's square root both sides. And that would mean that x plus 2 is equal to plus or minus 3. And that's true. So then you know that x plus 2 is 3. Subtract 2 from both sides. That would mean that x is 1. Or that x plus 2 is negative 3. Subtract 2 from both sides, you get that x is negative 5. And now all of a sudden we kind of go back to our picture and we look at it and we go, that kind of makes sense. Let's see if I can get it. Okay. We say, there we go. We said we guessed that there was going to be one of the values was going to be somewhere over here, and that's this one, that x is 1. And another value was going to be way further negative back here, and that's this value, x is negative 5. So wow, that kind of makes some sense. Okay. So that each one of those points, whether we be at negative 5, 1, or whether we be at 1, 1, we're saying that those points are square root of 13 away from this point, negative 2, 3. Okay, let's keep moving. I'm sorry, I don't mean to bog down and slow down, so I want to keep zipping through this. I just want to make sure you guys feel very confident about the things you're working through. So let's try to finish well. This one right here, it says, hey, make sure this is on the unit circle. Remember, the unit circle was a circle with the equation x squared plus y squared equals r squared, which is, in this case, 1, okay? And so to make sure that this is on the graph of the unit circle, we just have to plug in the values. Plug in the x's, plug in the y, and then we'll get it. So you say, well, is it true that 1/2 squared plus negative square root of 3 quantity squared is equal to 1 squared? Well, that is to ask yourself, is 1/4, let's see, negative square root of 3 times negative square root of 3 would give me 3, 4. So is 1/4 plus 3/4 1? Well, yeah, because 1/4 plus 3/4 is 4/4, and that is 1. And so that's an easy way for us to show how that is on the unit circle. Now, number 12, you didn't have to do, so don't be freaking out. But it did ask, hey, what are some coterminal angles to 225? And I just wanted to do a quick reminder and review that coterminal angles, to find those, we would always just either have to add or subtract any multiple of 360. So if I have 225, and I take 360 and add them, and I get 585, 585 is coterminal to 225. Or if I take 225 and I subtract 360 and I get negative 135, negative 135 is coterminal to 225, which means the angle has the same terminal side. They share the same terminal side. Now, make sure what was super important is that negative 135, not positive 135. You can't just go, well, the negative sign doesn't matter. It matters a ton. And so that absolutely matters in this case. Okay? All right, we're on the home stretch. We're going to rock out these last few problems, and it's going to be really easy. First of all, we said if cosine theta was negative 1/2, what quadrants could it be in? Well, you got to remember, cosine theta is x over r. R can't be negative, so in this case, the only way it's going to be negative if its x is negative. So in terms of my quadrants, x is negative over here in quadrant 2, and x is negative here in quadrant 3. So that's my answer, quadrant 2 and quadrant 3. The next question said, well, what if cosecant were positive or greater than 0? And what if cosine theta was less than 0? Well, for cosecant theta to be greater than 0, remember cosecant theta is equal to r over y. So that would mean that, since r is always positive, that would mean that y has to be positive. So we're going to think about that. Where is y positive? Well, y is positive in both these quadrants, quadrant 1 and quadrant 2. And then we look at the second part. So what about cosine theta is less than 0? And cosine theta is x over r. So if that's negative, the part that would be negative is the x. And so that x is negative over here. So where do those two overlap rather? They overlap right there. And so then we would know the answer is quadrant 2. The only spot on the coordinate plane where cosecant theta is greater than 0 and cosine theta is less than 0 is quadrant 2. All right, now we're really on the home stretch. Okay, we were given a problem that said, hey, the theta passes through this point, -3, -1. Well, you take that and you plug it into the x squared plus y squared equals r squared, because we're given x, so we can plug that in. We know that's 9 plus 1 is equal to r squared. So therefore, r squared is equal to 10. R is equal to the square root of 10. Once we have that, we can get all of the trig functions. We know that sine theta is y over r. So in this case, that's going to be 1 over square root of 10. Or I'm sorry, -1 over square root of 10. Cosine theta is x over r. So that's going to be -3 over square root of 10. And tangent theta is y over x. And so y over x in this case is going to be -1 over -3, which is 1/3. And then for these others, we just have to flip them. So cotangent theta is 3. Secant theta is negative square root of 10 over 3. And cosecant theta is negative square root of 10. Okay? All right. Number 20. Number 20 says, okay, we've got the sine of theta is 1/2, and we're in quadrant 2. So if sine theta is 1/2, and this one, it doesn't actually specify whether you got to do it by identities. It just says, hey, this is the deal on number 20. Find the remaining trigonometric functions of theta if sine theta is 1/2 and theta terminates in quadrant 2. This one, man, I say let's use identities. Cosine theta is equal to the plus or minus square root of 1 minus sine squared theta. So now in quadrant 2, we know that cosine dealing with x is going to be negative. So I can kind of take that part out of it and say, well, I know it's going to be negative. Square root of 1 minus, we're going to take this and we're going to square it. 1/2 times 1/2 is 1/4. So 1 minus 1/4, that's the same thing as 4/4 minus 1/4, which would make this a negative square root of 3/4. I know the square root of 4, so therefore cosine theta would have to be negative square root of 3 over 2. And once I have that, I'm going to go ahead and write down all 6, even though it only asked me for 3. Sine theta is 1/2. Cosine theta is negative square root of 3 over 2. Tangent theta, which is sine theta over cosine theta, the denominators cancel out. That becomes 1 over square root of 3, but make sure the whole thing's negative. Cotangent theta, we flip that, we get negative square root of 3. Secant theta, we flip cosine theta, we get negative 2 over square root of 3. And cosecant theta, we flip that and we get 2. All right, number 21 is one of my favorite types of problems because with this one, it's our connection between tangent and algebra 1. And we remember that tangent theta is equal to slope. And so I look and go, okay, the slope of this one is -2. All right, so therefore tangent theta is equal to -2. It says we want to be in quadrant 4. Why does that matter? Well, because if tangent theta is -2 and tangent theta is y over x, if it's negative, it means one of them is negative. But I got to know which one. And in quadrant 4, x and y is positive negative. So it must be my y that's giving that negative value. Now, again, it didn't say you had to use trig functions or trig identities to find the other trig functions, but I like using identities. And so I would say, well, I know that secant squared theta is equal to 1 plus tangent squared theta, which is to say secant squared theta is equal to 1 plus, I'm going to square that negative 2 and I get positive 4. So secant squared theta is equal to 5, which means that secant theta is equal to plus or minus square root of 5. So which one is it, positive or negative? Well, for the x, we know that we're dealing with positive, all right? And so therefore we look at this and we say, okay, secant theta is equal to positive square root of 5. And so I know that tangent theta is negative 2, which would mean that cotangent theta is negative 1/2. I know that secant theta is equal to square root of 5. So therefore cosine theta is equal to 1 over square root of 5. I know sine theta has the same denominator as cosine theta. So it's going to be square root of 5 on the bottom. And if this one's going to be negative 2 over 1, if this numerator, or if that showed up right there, then this shows up right here. Okay? And then, therefore, my cosecant theta, I flip this, and I get square root of 5 over negative 2. Okay, almost done. Secant theta is 3, quadrant 4. Secant theta is 3. All sorts of different ways of doing this. I know that I'm just going to do it the same way a student in one of my classes did. They looked at it and they saw it like this. Secant theta is 3. Well, square that, you get 9 is equal to 1 plus tangent squared theta. Subtract the 1, and that would mean that tangent squared theta is equal to 8. So therefore, tangent theta is equal to the plus or minus square root of 8. In quadrant 4, tangent theta is negative. So tangent theta is equal to negative square root of 8. So if I'm doing my 6 trig functions, I know that tangent theta, negative square root of 8, which would mean that cotangent theta is negative 1 over square root of 8. Secant theta is 3, meaning cosine theta is 1/3. Sine theta always has the same denominator, something over 3. So this is over 1. This showed up here, so this shows up here, negative square root of 8. And then for cosecant theta, we flip it, and we get 3 over negative square root of 8. All right, last 2 problems, the trig identity problems. Couldn't get any easier. What is cotangent theta? Cotangent theta is cosine theta over sine theta. What is cosecant theta? 1 over sine theta. With these, you got to be able to flip and then multiply. So you get cosine theta over sine theta times sine theta over 1. When you do that, these cancel out, and you're left with cosine theta equals cosine theta. And for this one, you've got cotangent theta plus tangent theta. Well, cotangent theta is cosine theta over sine theta. Tangent theta is sine theta over cosine theta. And for these, you think common denominator. This one has a sine theta in the denominator. The other one has a cosine theta in the denominator. The only common denominator of those is the product of them. So I say, well, this one's got to get what it doesn't have. It doesn't have a cosine theta in the denominator. So I'm going to multiply the top and bottom by cosine theta. This one doesn't have a sine theta in the denominator. So I'm going to multiply the top and bottom by sine theta. And what does that do? Think about it. Well, that makes this a cosine squared theta over cosine theta sine theta plus sine squared theta over cosine theta sine theta. Now remember, you can multiply in any order. You can add in any order. So that it doesn't matter if I switch a couple of these little things around like I did here on the bottom. Okay. Let me give myself just a little bit more room. Oops, I stole some things. Okay. All right, so at this point, the whole point of finding common denominator is to bring them all together. And so that would say cosine squared theta plus sine squared theta all over cosine theta sine theta. That top we should clearly recognize as 1. Cosine squared theta plus sine squared theta is always 1. At the bottom, we have cosine theta, sine theta. And then we can split that. So it says, we kind of break it up just a little bit, where it says 1 over cosine theta times 1 over sine theta. And what is 1 over cosine theta? Well, that is secant theta. 1 over sine theta is cosecant theta. And that is the very thing we're trying to get to initially. Okay. Awesome. Okay. Well, I hope you guys are feeling prepared. If there's any part of this video you need to rewatch, please do that. Good luck. You're going to do great. You have plenty of time. When the bell rings, we're done. You guys have a great day. Bye-bye.